These are the graphs of some functions, and we call them the basic functions because they certainly are not the only functions, but they're the functions a whole lot of stuff is built on that you've had so far. So this is a day that we go back and analyze them, and here are some analysis sheets for you. Okay. See, if you have, I'm going to write these the way you're more accustomed to seeing them. This would be like y equals 1.5. Y equals 1.5. It's a horizontal line going through the y-axis at 1.5. All right, here we've got the function y equals x. This is like the mama and daddy of all straight lines. Y equals x. And you can see that the domain and range and increasing on and constant on and decreasing on and all of that is there as well. And then some things you don't know about odd and even functions. This is the absolute value function. As you can see, the outstanding thing about the absolute value function is it comes to a sharp point. So to that extent, it's different from y equals x squared. Okay. Yeah. Now, y equals x squared and the absolute value of x behave pretty similarly, but not exactly alike. This is shaped more like a U, and this is always shaped like a V. The absolute value function always comes to a sharp point, and the even when you have a really skinny parabola, it does not come to a sharp point. Here we have y equals the square root of x. Notice, well, all of these are in their home positions. So in its home position, it starts at 0, 0, and rises to the right forever and ever. This is the graph of y equals x to the third. Y equals x squared and y equals x to the third are proved to be very important last time when we discussed end behavior, also called the leading term test. In this book, in this version of MyMathLab, they call it the leading term test. But what does the function do out on the ends? And as we said last week, that's based on y equals x squared. And y equals x to the third. Then we have the cube root. And it's kind of like that. It's not really flat, but it's one of those cases where it is slanted, but it gets so close to the y-axis that you can't really see that it's slanted. Okay, so these are the functions we're going to be working with the first part of today. Nope. Here's what we're going to be dealing with. These are, like I said, these are in their home position, but how boring would it be if they just stayed there all the time? So what we're going to do today is talk about how it's a lot like writing computer code. How do you code these functions to be seen in different places? That's what we're going to talk about. This is what we're going to talk about. And I'm going to need this. All right, here we go. We're going to talk about how to shift those functions that we just saw up and down. So let's look at y equals x. Well, I would rather have that black. Let's go to y equals x. I'm going to graph it real fast. Y equals x. That's all there is to it. And there's the line y equals x in its home position. Notice the home position most of the time has it crossing at 0, 0. Well, how can we move it? Vertical shifts can move it directly up and directly down. That's all a vertical shift does. Can be a little boring. So suppose I have, and for those of you who have had this before, well, actually it's covered a little bit in intermediate algebra, but not a whole lot. If I want to shift this graph right here up 3 units, then the way I code that is with a +3 on the right end. Okay, so if we wrote this as f of x equals x, then this function would be f of x plus 3. Here's the f of x part.
Professor?
Yes?
What do you mean by the right end?
I mean, it's at the right end. Thank you. The vertical shift thank you for asking. If you've got a function and you want to shift it up 3 units or down 3 units, then where you write that, regardless of what this looks like, is with a +3 out here on the right side, the far right side. That's where you write it. So for instance, if our f of x is all right, and up 3 units, shift up. Okay, if we have f of x equals x, then to shift it up 3 units, on the right-hand side of the x, I would write +3. And if we have the function f of x equals the square root of x, and I want to move that up 3 units, I would write the square root of x, that's the function, +3 out here. And that's the meaning of that. How about the absolute value? If I want to shift that up vertically, I would type the function and then put a +3 out on the right side. That's what I mean.
So what if X was on the left and Y was on the right? Would we then write it on the left?
To write something as a function, you've got to have Y on the left.
Okay.
Okay, so anyway, that's what I'm going to do right here, except it disappeared. I'm going to go back to Y equals 3 and come down to Y2, and I'm going to type the function Y equals X, but then to move it up 3 units, I put a +3 over there. And what that does is vertically shift this up 3 units. And that's called a vertical shift. Now, let's move on to this. Here's Y equals the square root of X in its home position. Oops, I don't want it there. Second X squared, X. Okay, there's Y equals the square root of X in its home position. If I don't want it there, if I want to shift it up 5 units, then I'm going to make a new function, because it wouldn't be the same as the old, that has the square root of X plus 3. 5. I wanted to shift it 5, didn't I? I'm getting bored with 3. I'm going to come over here and come out to the end, to the far end. You have to not be under the function, but at the far right end. Plus 5. Do you see how the plus 5 is not under the square root radical? And there it is up there. I moved it up 5 units. And we can do the same thing for down. For instance, suppose I want to graph X squared. Okay, X squared, Y equals X squared. Probably the most familiar graph to students. Suppose I want to shift that down 5 units. So if f of X equals X squared, and I want to shift it up 5 units, I would make another function. X down. I want to go down, don't I? Down would be minus. Okay. So I come over here. No, I don't do that. I go there. I come down to Y2, and I'll type X squared minus 5. And then I hit graph. And there it is. Here's Y equals X squared in its home position. And here's Y equals X squared shifted down 5 units. So since vertical means straight up or straight down, all I've done is I've taken this and I've moved it down. And so that's the way it is with all functions. Suppose I want to graph y equals x to the third. Or how about the cube root? We need to practice the cube root. Go to Math and cube root and x. Now it's important that you come to the outside of the radical because vertical shifts are never under the function part. They're always out at the right end of the line that you're writing. So you people with the older operating system need to close your parentheses there. People with this system have to click on the right arrow key to make sure you're not under the cube root radical. And if I want to shift this, well, let's look at it in its home position first. There it is. Now, if I want to move that up 4 units, then again, I'll type that, and this, and this, and right arrow key plus 4. Now, suppose I also want to drop it by 4 units, vertical shift down 4 units. Then I would type math 4 x, either right arrow key or close parentheses, minus 4. Graph. And there you go. That's what vertical shifting is all about, and that's where you write it. And this is the symbol for taking any function and shifting it up 3 units. F of x plus 3. With the plus 3, see, all the function stuff would be written here, and then you'd have a plus 3 stuck out on the end. Or a minus 3, depending on what you're doing. Here I would have the cube root of x moved down 4. That's not negative, that's a minus. But I'm trying to make very clear that this is not under the radical. Go ahead.
So do we need to put, is it x under the square root or under the cube root, or 3?
Yeah. There you go. Don't know why I did that. Guess I had 3 on the brain. Okay, clear. Clear. Those are the very easiest transformations. Moving directly up, moving directly down. Okay.
Am I doing something wrong to get an error message on the cubed problems?
Maybe. I would have to see what it is you're doing. Let's keep on trying. What does the error message say?
It just says quit.
Uh, Does it ask you, does it give you any other choice?
Let me try another one real fast. It just says 1 for quit or 2 for go to.
Do 2. Click on 2. So where's it going?
Then it just goes back to where you can plot the points.
Well, now, what do you mean?
Or where you can go in and put where it has y1 equals the same screen that you're on.
Okay, but y1 equals what for you? Because that's what's giving you the error.
I put 3 cubed square root x minus 3.
So where on the line is the cursor blinking?
Under the square root on the x.
Well, actually, it's a cube root.
Or yes.
I don't know why. Did you click on this button right here?
Oh, I did not. So maybe that's the problem.
I bet it is.
Yep, that's the problem.
Very good. Very
Thank
good.
you.
I've done that because that looks like an X, the times button. All right, now I'm going to write our basic functions here. The ones that have X's in them. Y equals X. Y equals, well, Y equals X. Y equals X squared. Y equals the absolute value of X. And we need to spend more time here so you can learn where that is also. Y equals X to the third. I'm going out of order from that sheet, but I'm kind of going by memory here. Y equals the square root of X, and Y equals the cube root of X. My goal is to stretch these. Stretch them up. Now let's see what I mean by that. So really the easiest one to do, I'm going to do X squared first because you'll see. So cool, there's our basic graph. Now I want to stretch this. Suppose you have a toy bunny and it's elastic and you're pulling it. Or you've got knee socks that have drawn up and you're trying to stretch them up to your knee. That's what I'm going to do to X squared. And how I do it is this. However much I want to stretch it, let's make it 3. Stretch. Now I'm going to write this the way your book often does. Stretch by factor of 3. okay? This is how I'm going to write it. Y equals 3 times x squared. All right, and look what happens. It's as though this graph has gotten stretched up. Notice that none of the x coordinates have changed. 0, 0 is still at 0, 0. But it's like an invisible two hands came down and stretched the line up. It does that by taking all the XY points and multiplying the Y coordinates by that 3. That's what's really happening. There aren't any invisible hands pulling it up. Really, this 3 is multiplying all the Y coordinates in Y equals X squared. Now, I can show you. If X equals 1, in the basic graph, we have the point 1, 1 right there. But in Y equals 3x squared, we have the point X equals 1, Y equals 3. So that would actually be the difference. So here, the point 1, 1 changes to 1, 3. And the point 2, 4 changes to 2, 12. The X coordinates stay the same, but the Y coordinates get multiplied. So over here, the point 39 becomes the point 327 because 9 was multiplied by 3, and so on. If I want to stretch Y equals the absolute value of X, three units. Or what? Who says we have to do it 3? Oh, because I wrote a factor of 3. Okay. Y equals 3 times the absolute value of X. So let's graph the absolute value of X by going to Math. And then it's not there. Imagine. So we have to hit the right arrow key to go over to Num. And there's ABS for absolute value right there at the top. So I click Enter. There are my absolute value bars. I'll type X. And then my right arrow key. Or if you show ABS parenthesis and you type X, you have to close your parenthesis. All right, so here is the absolute value of X in its home position. Now, to graph 3 times the absolute value of X, that is, to vertically stretch this graph by a factor of 3. 3, Math, right arrow key, Enter, X, and then come to the outside. There. It's as though somebody took this, like old-fashioned rabbit ears that people used to have on, stretched it up. And the same thing would be true of these. To stretch this up and make it more vertical. Clear, clear. Okay, to graph y equals x to the third, I type x caret 3. And then to come down, you hit the right arrow key. Just like in MyMathLab. There's y equals x to the third power. Y equals x cubed. Now, if I'm going to stretch this by a factor of 3, I come down here and I type 3, and then x caret 3. See, it got stretched. So it's higher for all intents and purposes, and lower. It's closer to the y-axis because it got stretched. And to stretch this would be y equals 3 times the square root of x. And to stretch this, you would have y equals 3 cube root x. Well, if you can stretch them, you can shrink them. Well, let's talk about what is it that stretches the functions, the graphs of the functions. What is it that stretches the graphs of the functions? Well, the fact that this number the number in front of the function is a number greater than 1. So if we wanted to write it as some kind of formula, we would have a times f of x. And if a is greater than, strictly greater than 1. If a is 1, then there is no vertical stretch. It's just the regular function. But this number is greater than 1. You could put 5 million. That'd be terrible, but you could. Now, how can I shrink it? Well, if I wanted to shrink my functions, shrink by a factor of, let's say, 1/2. And it's easier to write it as 0.5. 1/2 and 0.5 are the same. Then for y equals x, I would have y equals 0.5 x. If this number is between 0 and 1. So for a times f of x, let's write it up here. A times the function, so you've got a number multiplying the function. Now that number is going to be between 0 and 1, but not equaling 0 and not equaling 1. In other words, it's a fraction.
Professor,
Yes,
could we not achieve the same effect by dividing by 2?
we're going to get there.
Okay.
So y equals x squared. That would give us y equals 0.5 x squared. Let me get rid of that a over there. And you could keep doing that with any number smaller than 1, but positive. Y equals x to the third. Y equals 0.5 x to the third. We're shrinking this by a factor of 1/2. Y equals the square root of x. Y equals 0.5 times the square root of x. So let's actually do that so you can kind of see. Here's y1 equals the square root of x. Okay, now I'm going to stretch it by a factor of 3. So let's go back up here for a minute. Three square root of x. There you've stretched it up. You haven't lifted it up. It's not a vertical shift. 0, 0 is still at 0, 0, but it's like you stretched it up. And if I want to shrink it by a factor of 1/2, 0.5 square root x. Here, look at it, it's all shrunk down. The x coordinates are in the same place. But now, for instance, in y equals the square root of x, the 0.11 is now the 0.1/2. This number, whether it's big or little, multiplies all the y coordinates and leaves the x coordinates completely alone. So we've talked about a vertical shift where you physically move the graph up and down. And a vertical stretch and shrink where you keep the graph in the same place, but you stretch it up or you shrink it down. Now, I've gotten so paranoid over the last week. I want to make sure I'm recording. Yes, it says you're recording. Okay. All right, well, what else can you do with this little bugger? You can reflect it. And these vertical shifts, vertical stretches and shrinks, and vertical reflections are the easiest. Because once you get to the horizontals, it becomes decidedly more difficult. So you're going to love the verticals and hate the horizontals. But let's get to the last vertical we're going to talk about. Here's our list of basic functions. Y, well, we're not going to do y equals c, but y equals x, y equals x squared, y equals the absolute value of x, y equals the square root of x, y equals the cube root of x, 1, 2, 3, 4, 5. And I know I've left out some, but that's good enough. We are now going to reflect these guys across the x-axis, which also can be thought of as just flipping them upside down. So clear, clear, clear. Y equals x squared shows this beautifully. They all do. Y equals x squared. Here's our basic y equals x squared graph. If I want to reflect this across the x-axis, and that's the name of what we're about to do, reflection across the x-axis. In other words, make it go upside down. There's y equals x squared. Let's flip it upside down. I'm going to go down to y2. I'm going to put a negative, not a minus, a negative sign. X squared. No. We just turned it upside down. Yep, that's all it is. If I want to reflect any function vertically across the x-axis, we'll rewrite this as y equals negative x, y equals negative x squared, y equals negative the absolute value of x, y equals negative the square root of x, and y equals negative the cube root of x. And you can turn it upside down. Okay, now, here's something very, very important. A combo. That's my name for it. Suppose your basic function is y equals the square root of x. And then we can let that be y1, and suppose then I make y2 equals negative 3 times the square root of x. You would be tempted to say that the vertical stretch is negative 3. Vertical stretch is negative 3, it's not. So this is a very big deal, and you will encounter it on the test and on the final. That negative sign in front is always a reflection across the x-axis. Always. It is not part of the vertical stretch. What you have here is two transformations working on the same function. And you're going to have a lot more. That negative sign is the reflection across the x-axis. And the 3 is a vertical stretch. So don't get trapped. That's a very common error. Okay, so those are the vertical transformations. We have a shift up and down. We have a stretch and a shrink vertically. Vroomp, vroomp. And we have a vertical reflection, kaboom, upside down. These don't affect the function itself. A square root is still a square root. Notice that x squared stays the same. The absolute value of x stays the same. The square root of x stays the same. The cube root of x stays the same. The action is occurring either in front with the reflection across the x-axis, or the shrink, or the stretch. Those occur in front of the function itself. So that you could just as easily say 3 times f of x, like we did here, or 0.5 times f of x, or negative f of x, or in this case, negative 3 times f of x. F of x stays completely intact. So a vertical shift up would be f of x plus 3. A vertical shift down would be f of x minus 5. The function part stays entirely the same and is not affected by vertical movement or vertical coding. It's not the way it is with horizontal.